Why do some instruments sound different even when they're playing the same note? Well, first we have to ask, what is sound? The answer to that is actually pretty simple. Sound is just variations in air pressure over time. Any sound, whether that's a conversation or a song, can be recorded solely on a 2D graph. One axis as pressure, the other as time. So how do we perceive different pitches of sound? Well, the pitch of sound is described by its frequency. The frequency of a sound wave is the amount of times a given layer of air molecules oscillates per second. A higher frequency, aka more frequent oscillations, is perceived by our ears as a higher pitch. Okay, so now we know that sound is variations in pressure, and we know that frequency is how often or how fast those air molecules oscillate. But I haven't really said anything about the nature of this oscillation. In the graph, their oscillation is sinusoidal, but it could be some other shape, so long as a repeating unit, called a waveform, occurs periodically. Let's take a closer look at a physical example here to see what's going on. Consider a string being plucked. You might think that the string behaves like this, but in real life it might look something like this. So what's actually happening? The answer is that in addition to this fundamental frequency, the string also vibrates multiple different frequencies called harmonics. But how is it possible for the string to vibrate in different frequencies at the same time? For that, we need to go back to the basics. Let's start with the fact that sound is a wave. A wave is a disturbance that transfers energy from one point to another through a medium. In the case of sound, the medium is air molecules. For now, we'll use the example of a rope because it's easier to visualize. What happens when two waves travel towards each other on the same string? Well, when they meet, they'll be in a superposition. It might sound complicated, but it's actually pretty simple. When two waves overlap, the resulting wave is their sum. We call this a superposition of wave 1 and wave 2. You might have heard of superposition in quantum mechanics as something being in multiple states at once. It's not really rigorous, but it's a good way of thinking about the superposition of mechanical waves. A string fixed at both ends vibrates in standing waves, which are called that because they don't appear to move. There are many different modes in which these standing waves can vibrate in. By itself, each one would sound like a pure tone at a different pitch. When a string is excited, all of these modes will sound. Each will sound at a specific intensity depending on how the string is excited. The final motion of the string is a superposition of all of these harmonics, which brings us back to this final motion. But still, the intensity of the harmonics on the string is not necessarily how loud they are to us. The body of a violin, for example, does not transmit all harmonics into the air equally as well. In general, some frequencies are radiated much more efficiently than others because of an instrument's shape and material. The final waveform that we hear is a sum of multiple pure sine waves with different frequencies. And in fact, any shape of waveform can actually be constructed as the superposition of different frequencies with specific intensities through a mathematical process called a Fourier transformation. The final sound can also be represented on a graph called a harmonic spectrum, which shows us the intensity of each harmonic that sounds in the air. For a single note, this will look different for different instruments. For example, higher harmonics sound more strongly in a piano than a flute. This is also why instruments in old records don't sound like they do in real life. Old recording technology, microphones, and speakers change the balance of these harmonics, which changes the timbre. And while the sound isn't perfectly faithful to the original performance, the old-timey coloration is exactly what many people say they love about records.